Hi, everybody. It's Dr. White here, ready to discuss the situation of two or more random variables, particularly if they're all independent of each other. So, in general, a multivariate random variable would be a random n-tuple, an ordered tuple with n elements, capital X1 through capital Xn. And so just like bivariate random variables, they have PDFs, or if they're of continuous type, they'll have PDFs, or if they're of discrete types, they'll have PMFs. We'll just call them F of X1 through Xn. And the support for these things is going to be some subset of n-dimensional space, Rn, the set of all ordered n-tuples where you could have any real number in each of the spots. Okay. How might expectations work, mathematical expectations? Well, let's just imagine any transformation of x1 through xn. So the u here is some real valued function on n variables. So it comes out one number, but it's given n numbers to work with. And so the result is a new random variable y whose mathematical expectation you could ask about. So one way to work it is certainly try to find the marginal PDF or PMF for y, by working with the joint and, integrating in one of the dimensions to get the, working with a joint and setting up transformations and working some change of variables or CDF technique to get the marginal. Now, if you're going to be doing the change of variables technique, then you're working on a change of variables where there's maybe more than bivariate. And so you might be working, instead of a 2x2 matrix to get a Jacobian, you'd be working with like an n-by-n matrix, and things get hairier computationally. And we're not going to get into any of that in this text. In fact, this can be kind of a slow way to work because there's this alternative way to work. Instead of doing that, finding the marginal and then just applying the straight up definition of expected value, that would involve a sum, or it would involve an integral depending on whether it's discrete or continuous. Instead of that approach, then what you could do is what we have been doing with functions of random variables to find mathematical expectations, where we just integrate over the entire sample space of the multivariate situation. So expected value of y would be some sum or a bunch of integrals, depending on whether you're discrete or continuous. But either way, they got to cover the whole sample space. Possible values of the little y times the chance of getting each of the exact x1 through xn's that fed into that possible value. So this fact that the expected value could also be computed by this multivariate sum is not proved in the textbook. And I'm not going to prove it in the notes. The proof is not that difficult, but it's just kind of unenlightening. So instead, later on, I'll do a computational example that where we can kind of look into it and gesture at how such a proof would have to go. And you'll see for yourself that the kind of housekeeping that would need to be done would be kind of boring. Well, one particular case is where your y, your u of x1 through xn, is just one of the x's all the time. So like maybe u of x1 through xn is xi, like it might be x1 or x2 or something. So you could get the expected value of any one of those random variables by summing up over the entire sample space possible value times the PDF or PMF. A very common transformation of the x1 through xn is when capital Y is what we call a linear combination of the xi's, a sum of the product of a constant times xi, and you can change your constant with your xi. So the a1 through the an here are just fixed constants, and each one is multiplying its own random variable, and then you're adding them together. That's called a linear combination. So like 2x1 plus 5x2 would be a linear combination of x1 and x2. 17x1 minus 2.5x3 is a linear combination of x1 and x2 and x3. It's just that the number in front of the x2 was a 0. So if you needed its expected value, you would be summing over the entire sample space possible values of the y times the f. And I would just like to look into that and like see what that works out as. And I'm going to do that as soon as I get my coffee. Okay. So how might this sum work? So you've got, a sum of these sums right here. But you know how sums work in summations, commutativity of addition, you can break it up and group them differently. So instead of like adding these things together and then doing the sum over all the possible, x's, what I could do is just do the ax1s and add them all up. And since the a1 is a constant, it could be factored outside of those sum signs by the distributive property. So that's where I'm adding up all of the a1 x1s. And then I could also add up all of the a2 x2s. And then I could add up all the a3 x3s, all the way up to adding up all the an xn's. And again, because the an's are constant, they don't change as possible values of xn change, then we can pull them out of the sum sign. And so when we look inside these sums here, we see that they are precisely the definitions for the expected value of x1, expected value of x2, all the way up to the expected value of xn. So a summation way of writing that is sum I goes from 1 to n, ai times the expected value of xi. Now for short, I'm going to let the expected value of xi be called mu I. And so we get this expression. Expected value of sum of ai xi is sum of ai mu I. So the expected value of a linear combination is that same linear combination of the expected values. That happens no matter what, x1 through xn you've got. If all the AIs are 1s, then your linear combination is just the sum of the xi's. And so this formula would come down to saying just that the expected value of a sum is sum of expected values. So that's actually a fact that we've been gesturing at and even letting ourselves use occasionally over the previous course of the semester. But this is the first time we've actually given a formal argument for it. Okay, next up, let's say that the variance of xi is sigma I squared for short, for each of the i's from 1 to n. Okay, I'm wondering, like, what would be the variance of that linear combination? What's the variance of the sum I goes 1 to n ai xi? Well, variance, by definition, is the expected value of the random variable minus its expected value squared. Okay, so it's the expected value of this stuff. Here's the variable, minus here's the expected value of it according to the formula we just proved. And we're squaring, and then we are taking the expected value of that new random variable. Now, when I look at this sum minus this sum, I could just as well subtract off the ai mu i's from their corresponding ai xi's and then add up. It's just commutativity of addition, moving things around to get this. And then I would need to square that sum. Okay, so let's think about what's it like to square that sum. That sum has n terms. It's got an a1 x1 minus mu1 term. It's got an a2 times x2 minus mu2 term, and so on to an an times an xn minus mun term. It's got n terms. Now it's being multiplied by itself, so imagine two things written out in front of you. The sum of n items, n terms, in parentheses, times, in parentheses, that same sum. And you got to multiply them out. And so you FOIL it out slowly. And what you've got to do is extract an item from the first sum and an item from the second sum and multiply them together. And you've got to do that for all the ways of grabbing an item from the first sum and an item from the second sum. How many such ways are there? Well, there's n ways to grab a term from the first sum and n ways to grab a term from the second sum. So by that multiplication principle from way back, it's n squared ways. And so when you FOIL it all out, you are going to end up having a huge sum of n squared things. And here's how they'll look. You could grab like the ith term from the first sum and the jth term from the second sum. And so you'd have to multiply the ai xi mu I by the aj xj mu j. And you just do that for all of the first terms, I going from 1 to n, and all of the second, j goes from 1 to n, and add together. So that here is a FOILing out of this square here. Now, let's think about this. Expected value of sums is sum of expected values. Well, let me put it this way. We're looking at a linear combination of random variables. Our random variables are the xi minus mu i's, xj minus mu j's. The constants multiplying them are the ai aj's. And we're just adding together. It's a linear combination of those. And we know that the expected value of a linear combination is that same linear combination of their expected values. And here is that fact expressed. The linear combination of the expected value of that product, xi minus mu I, xj minus mu j. This fact that we're using here so much, that the expected value of linear combination is linear combination of expected values. That fact is often stated by saying that expectation is a linear operator. An operator is something that goes from stuff to numbers. And whenever it has the property that the operator applied to a linear combination of stuff is the linear combination of the operator applied to the stuff individually, then your operator is said to be a linear operator. Well, anyway, let's take a look at what we've got now. Hey, that is the definition of the covariance of xi and xj. So now the variance of y is expressed as that double summation. Now, sometimes the I will be the j in that sum here. Like the L will be 1 and the j will be 1. The I will be 2 and the j will be 2. That'll happen. And in that case, the covariance of xi, xj could just as well be said to be covariance of xi, xi, because j is I. And so the covariance would look like that, which is just the expected value of xi minus mu I squared, which by definition is the variance of xi, sigma I squared for short. Now, when I is not j, it's not so nice, But, we defined something called the correlation coefficient between two random variables x and y, and we defined it to be the covariance of the x and y divided by the product of their standard deviations. So I'm going to go ahead and define rho ij to be the covariance of xi xj over sigma I sigma j. And then you could write the covariance of xi xj as rho ij sigma I sigma j. So in total, the variance of y, the variance of that linear combination of the xi's, you could break it up into the parts where the I was the j. And so you'd have your AI aj, which is ai squared, times that sigma I squared we found here for the covariance. And then we have the other parts where the i's are not the j's. And then you've got the AI aj like before, and the covariance of xi xj, but we'll write that as rho ij sigma I sigma j. So there's a formula for the variance of any linear combination. Okay, let's start thinking in about what happens if the x1 through the xn are independent of each other. But what do I mean by they're being independent of each other? Well, I'm just going to generalize the definition for independence of bivariate. The definition will be that the joint PDF or PMF is the product of the marginals for all x1 through xn in Rn. And it can be proved off this fact, and it's just too much of a chore to bother to stop, but it can be proved that if x1 through xn are independent in that sense, then all pairs xij are independent in the bivariate sense. So let's think about what the covariance of xi and xj would be when xi and xj are independent. After all, that term shows up, in finding the expected value of the variance for linear combination. What's it like? Well, let's see. We have a shortcut for covariance that you might want to go back and review in the section where we define covariance. And I think that's section 4.2. So taking that shortcut formula, hey, remember that when random variables are independent, the expected value of their product is the product of their expected values. And so the covariance was 0. Remember when we proved that? So those covariances in this formula here, those covariances are going to be 0. These covariances are going to be 0 when the i's are not j's, because xi will be independent from xj. And so the rho ij's are going to be 0. And so if you look at this formula here, if the xi's are independent, then this term here works out 0. That just works out to be a sum of a bunch of zeros. And you're only left with this stuff. And so that's kind of neat. When the x1 through xn are independent, the variance of a linear combination of them is just the sum of the squares of the little constants in the linear combination times the variances. So a couple of special, one special case. Suppose that the AIs are all 1, so that your linear combination is just the sum of the xi's. Then this would give you the sum I goes from 1 to n, 1 squared sigma I squared, with the result that the variance of a sum is the sum of the variances of the random variables individually. So that's great, but it only works if the x1 through the xn are all independent. Now, we're quite frequently going to meet in the future, quite frequently going to meet the situation where the x1 through xn are all independent and they all have the same distribution. And in that case, they're called a random sample of size n. And in that case, there's also another random variable that you'll often be interested in. It's the sum of those xi's divided by n. And it's called x bar, or the mean of the sample. Now, let's think about the x bar, and I wonder, like, what's its expected value? Well, when I look at x bar like this, I could just stick the 1 over n, I could put it inside the sum sign by the distributive property, and it would be a linear combination of the xi's where the ai is a 1 over n each time. And so therefore, the expected value, since it would have to be the linear combination of the expected values of the xi's, it would be the sum, 1 goes to n, of 1 over n times expected value of xi. And so you could just factor that out. And these xi's all have the same distribution. So they all have the same expected value. I just need something to call that expected value, and I'll call it mu. So let mu be the mean of the common distribution that all these xi's have. And so I'm adding up n mu's here, but I'm dividing by n, so I really get it down to just mu, which kind of makes sense, if you grab from the same distribution n times, you're like trying a random variable n times, and you average up your results, you know to expect the average to be somewhere around the expected value for the distribution, and that's what this fact is saying. On the other hand, what's the variance of the sample mean? So that would be the variance of this linear combination. And so, since the xi's are independent, that would be the sum of the ai squared sigma I squareds. The ai squareds are 1 over n, so I get a 1 over n squared. The sigma I squareds are all the same because the distribution is all the same. So let's let sigma be the variance of the common distribution, and I get that expression that's shaded in. And so I get the same thing, just added up n times, so I get n of that same thing. So there's a little cancellation, and I get sigma squared over n. So that's the variance of x bar. Now remember, standard deviation is the square root of variance. So the standard deviation of x bar would be the standard deviation for the x that all these xi's share, divided by the square root of n. And so we're going to see later on the importance, the relevance of this. It'll help us to know that when we're sampling from some big population, where the mean of the population is mu, and the amount of spread in the population is sigma, that we can expect our sample mean to be mu, give or take sigma over the square root of n or so. And so the bigger our sample size, the less that give or take figure there. And so the more likely the sample mean is to be close to the mean of the population. So we haven't quite put all the machinery together to really talk that through, so we'll just leave it for a couple of sections from now. Well, it's been a lot of theory. Why don't we just do, a few examples? And frankly, a lot of the examples are common sense, but some of them really rely on the theory we've developed in a big way. Let's try exercise 1 here. Say that x1 and x2 are independent, and x1 is Poisson with a lambda of 2, and x2 is Poisson with a lambda of 3. They're just going to ask you a little question about the sum of x1 and x2. Like, what's the chance that it's 1? And this is really kind of just a check on, can you apply some basic probability ideas from way back, like make sure you haven't forgotten them. So you're wondering what's the chance of this event, and so you need to break this event down into things whose probabilities you can add up. And there's really only 2 ways to get this sum to be 1. When you got Poissons, their possible values are 0, 1, 2, 3, and so on. And so the only way to get the sum to be 1 is to have like one of them be 1 and the other one be 0, or the reverse. And that or there is an exclusive or. Those 2 events cannot occur together. And so the probability of the or is the sum of the probabilities. And let's take a look at this first event here, that x1 is 0 and that x1 is 1 and x2 is 0. So that's an and. We need a probability of an and. But the x1 and the x2 are independent random variables, so we can just multiply the probabilities for each one. The chance that x1 is 1 is the chance that a Poisson with lambda of 2 equals 1. And so I go to the formula for PMF of Poisson that's in my head and write that down. And the chance that a Poisson with a lambda of 3 is equal to 0 would be 3 to the 0 times e to the negative 3 over 0 factorial, which works down to that e to the negative 3. And then I do similar work for this probability of an intersection. And that one actually simplifies a little bit. I don't know if that's interesting or not. Okay, number 5. Let's say that x1 and x2 are a random sample from a distribution that has this probability mass function. So importantly, they are saying that x1 and x2 are independent. That's part of the definition of random sample. And both of them have that distribution that's shaded in there. Can we find the probability mass function for their sum? Okay, so let's do this. So one way to approach it is to first systematically write down all the ways you can get the different possible values of the sum. And that's what I'm doing in this first table right here. I'm thinking like x1 could be 1, 2, or 3, and x2 could be 1, 2, or 3. And in here, I'm putting what the sum of x1 and x2 would be. And so you can see that there's like a couple of ways to get a 5, and there's like 3 ways to get a 4. There's a couple of ways to get a 3. There's only one way to get a sum of 2 and only one way to get a sum of 6. Okay, now let's find the chances for all those ways. The joint probability mass function. Okay, because that's what they were asking for, So for that, they're asking for the probability mass function of y. I'm going to find the probability mass function for the joint situation, the bivariate situation, x1, x2. And then I'll go for y. So again, I think about all possible values of x1, possible values of x2, and what I'm going to write in here is little f of x1, x2, the joint probability mass function for capital X1, capital X2. So here's where I got to head back up to this table and use my independence. So like, what's the chance that x1 is 1 and x2 is 1? Well, the chance that x1 is 1 is 1/6. And the chance that x2 is 1 is 1/6. So the chance they're both 1 would be 1 over 6 squared, 1 over 36. Let's try another one of these. Like, what's the chance that x1 is 2 and x2 is 3? Well, let's see. The chance that x1 is 2 would be 2/6. The chance that x2 is 3, well, that would be 3/6. So I'd have 2/6 times 3/6 because of the independence. That's 6/36, which is what I have written here. And so each one of these little values is a product of the PMF values for the common distribution that the x1 and the x2 both have. Okay. Now, once we have the possible values for y lined out, and we've got the joint PMF lined out for the x1, x2, then we can go and try to get the marginal by doing some addition. So here are the possible values for y. And I'm sorry, marginal is not the right word. Let's get the distribution for capital Y by doing some adding up. So here are the possible values for capital Y. We found that here. Now we also notice, because of the repetition of some of these numbers, that there's going to be several different ways to get these values, and we have to add up the probability of these ways. So like, how can we get a 2? Well, there's only one way to get a 2, it was here. The chance of that happening was 1/36. So G of 2 is 1/36, no problem. But how about 3? Well, there's 2 ways for that to happen. This way, this way. And so we got to add up this probability and this probability. And so we get the 4/36. And we just do that for each of the other possible values of y. And so the circled values here are the G of y values for the probability mass function for capital Y. So that's the question they asked. I think they also asked to find the expected value of y, so let's go ahead and do that. Now that we've got the PMF for y, we can just add up over the sample space for y, so that's the integers from 2 to 6, y times G of y. And so, value times chance of value pulled off the table, and I get 168/36. Okay. Now, according to that theorem that is not proved in the textbook because the proof is too boring, you could also do a double sum over the sample space for the bivariate scenario with the x1, x2. You would just do possible values of y, x1 plus x2, times the PMFs for the joint. So that would mean that you've got to, consult this table here for your PMFs. And so let's give that a try. So like 2 was possible, and the chance was 1/36. 3 was possible, and that could happen in a couple of ways. When you're doing your sum here, you could be at the x1 is 1 and the x2 is 2, okay? And so then you get a 3. And what's the chance of x1 is 1 and x2 is 2? Oh, it's 2/36. Okay, so that gives this. Let's see, 4 is a possibility, right? And that could happen in several ways, one of which is where x1 is 1 and x2 is 3. And what's the chance of that? It's this. So you'll see what I'm doing here. There's a pattern to it. I'm looking at my possible values going across this row here. And then here's the chance of getting the possible value in the same way that I got that possible value over here. And then I could go on to the next row and say, okay, I could get a 3, I could get a 4, I could get a 5 in this particular way, like where x1 is 2 and x2 is 1. And then over here, I could read off the chance of getting the 3 in that particular way. And so I can just keep doing that for all of the 9 occurrences over here in this values table. Multiply those occurrences by the chances of getting them in those ways. And when you do that, you're going to end up with the same thing. And the reason you're going to end up with the same thing is like, well, take an example, like take the 4s. 4 times this, 4 times this, 4 times this. So that'll be 4 times this sum, here, here, here. But we met that sum up here when we were calculating the chance of 4. So a 4 times the chance of 4 actually is buried in that little piece right there. Similarly, 3 times the chance of 3 is buried. It's the sum of those two things. See? 2 times the chance of 2 is not buried too deep. 6 times the chance of 6 is not buried too deep. 5 times the chance of 5 is buried. It's broken up into those two, just like here. So really, you could formally prove that this double sum delivers the expected value by doing a lot of commutativity of addition and regrouping things and factoring some stuff out. And you could formally argue that that sum has to come out to be just this sum. And you could do that for any, sum of random variables, not just these two in particular. But you can see it would be kind of hairy to write down in general how to express that. And so the book doesn't bother, neither will I. I just hope this example has convinced you. Hey, let's try exercise 9. x1 through xn is a random sample from some common distribution with a mean of mu and a variance of sigma squared. And let's define y1 to be x1 and y2 to be x1 minus x2 and y3 to be x1 minus x2 plus x3. And we go on in an alternating way. So like yn could be expressed as the sum I goes from 1 to n minus 1 to the I minus 1 times xi. Check it out. Try it out for like n equals 3. And you'll see that it really does come to this. And what's the expected value of yn? So I got a little typo there. That should be a yn. So if you don't mind, I'm going to fix that now while I remember it. Well, the expected value of yn would be the expected value of this linear combination of the xi's. Okay. So that would be the linear combination of the expected values. And so that would be the sum I goes from 1 to n of minus 1 to the I minus 1 times a mu. And the mu is a constant, can factor out of the sum sign. And let's kind of think how that sum would work. Let's think about how this sum would work for various values of n. Like when n is 1, you're just doing minus 1 to the 0, which is a 1. When n is 2, you're doing the 1 minus 1, and that's a 0. And here's what you get when n is 3, you get a 1. When n is 4, you're going to get a 0, and you start to see the pattern. You're going to get a 0 whenever n is even. You're going to get a 1 whenever n is odd, so mu times it would be a mu. And so the expected value of yn, well, it's either going to be a 0 or a mu, depending on whether n is even or odd. It's pretty cool. What's the variance of that combination? And I see I need a yn there. Well, here it's most helpful that the xi's are independent. Then the variance of the linear combination would be the following linear combination of the variances, the minus 1 to the I minus 1 squared times the sigma squared add up from 1 to n. Now this time, you've got this thing inside the square that's a 1 or a negative 1, but you're squaring it. And so the result is that square is going to be a 1 no matter what. And so you're really just adding up sigma squared. I goes from 1 to n. You're adding n sigmas together. And so the variance is just n sigma squared. And so as n varies, the expected value of this thing, it just hops around between 0 and mu. But the variance gets bigger and bigger and bigger linearly with the sample size n. Kind of neat. Okay, so that's a few common sense exercises to get you started and applying the ideas of this section about means and variances of linear combinations of many random variables. Have fun with the homework problems in this section, and I will see you later.